a few years later, there was a competition of a question that was what was the longest title of a network calculus paper, and I won. And I tried to beat my own result. So the title is long, but in fact, I can do the presentation with one single slide. Okay, and if you understand this slide, you can go out to take a coffee. And if you don't understand this slide, okay, stay a minute if you want. Yes. So you all know, because you all know network calculus, that often we have some service beta, and we want to remove. Okay, no. We want to remove some interfering arrival curve. And in fact, up to Nancy, okay, people were often using linear approximation because implementing a staircase curve and so on requires, okay, we know now 4 years of work. Okay, so you don't always have 4 years of work to spend on some problem. Sorry, I really have a problem with this pointer. So what I say is that if you have, okay, sorry. So if you consider sporadic arrivals, okay, with staircase, the residual service that you will get is the complicated one here, okay? You go up and then stop and up and stop. And if you want to approximate your staircase function by linear one, okay, then when you do beta minus the linear approximation, you get, of course, a linear function, but you get the dotted one. That is not so close to the complex one. Okay, and what we propose is an analytical expression of the linear expression that is the dashed one. Okay, and that is computable in quadratic time, and that's quite the end of the talk. Okay, you know that all. Okay, residual service, non-decreasing closure, up closure, and so on. Linear arrival curve, okay, simple to implement. Also, you have an analytical expression, so you can use things like MILP, solver, and so on. But you do not represent very tightly a periodic flow because you do as if you can cut every packet everywhere, okay, which is not the case. Otherwise, you use a staircase arrival curve. But you have no analytical expression. So here is an example. One staircase function, another one. Of course, they do not have the same period, otherwise it's too simple. Then we do the sum, okay, and we can approximate this sum by a linear one. And in fact, there are equality points, meaning that you cannot do better. Then a beta function, and the beta minus the linear approximation, and then beta minus the staircase. And you see that you go up and down, okay? And you cannot do better, okay? I say because there are some points where there is an equality. But once you do the non-decreasing closure, okay, you change the game, okay, and you do really better. So that was the problem. What we have done, we have computed. We have an analytical expression of a rate latency function, which relies in between the residual service curve minus the staircase function and the residual service curve minus the linear function. We assume, of course, that the staircases are not whatever. They all are. We have a finite set of staircase functions that all are periodics. We also assume that the system is not overloaded because otherwise, okay. So what we did a pen and paper proof that is a generalization of a previous result, and we also did a coq proof. So that's the expression. Okay, I will not explain the detail. In fact, W. Okay, can I get W? Yes. W is the term that you get with the linear function. And, okay, sorry. And GL and GQ are two terms that you can remove and that are the gains that can shift up the residual service. Okay. L stands for linear because it can be computed in a linear time because we just took the mean of a sum and a maximum. Okay. And the quadratic, Q stands for quadratic because that's a double sum. So can you trust me? Okay. No. Of course, the fact that at first we had exactly the same result with just one slightly different expression on the jitter. Or say yes, we have also jitter. I don't. Okay, you know jitter. Okay, and we submit the first proof and. A reviewer find a mistake, so we write okay. And then a colleague of mine wrote a coq proof of that. So did you all know what is coq? So coq is a proof assistant. Sorry. Coq is a proof assistant, meaning that it is a tool that will check that your proof is correct, going into every picky details that you want to avoid to look at. Okay, so when you have chance, it can look there are some details that it can do automatically. You just say, okay, prove it automatically, and it can say yes sometimes, but in general, it takes time. So we did the proof with a pen and paper. It took me something like okay. Took me, in fact, 2 years before the first ID and the proof. But the proof is, I think, 3 pages long, 3 columns. Use 3 columns in IEEE format. Okay. It took 2 weeks to translate. Okay, no, 5 pages in proceeding. Yes, but that was ECRTS proceedings, so they are very long. Something like 2 pages in IEEE format. So it took 2 weeks to make the proof in coq. We found 2 mistakes in the proof and paper proof. One was a mistake in the proof itself, not in the result. When making some permutation, I was making some mistake between index and values. Okay, and in the first version of the proof, I was assuming positive and negative jitters, and in fact, we were not able to consider negative jitters. And the proof can be downloaded, and you can check it. Is there a gain with this result? So we generate a set of configurations. So each configuration is non-preemptive static priority scheduling server with a constant rate. Okay. We randomly choose periodic flow. So there are in the paper. So that's a published paper at ECRTS previous year. So you can find the details of the experiment. And we add flows up to reaching this load. And we are comparing two parameters, the tightness, not the tightness, the quality of the result and the time, the computation time. So here, how can you read it? We compute 4 bounds for a system. So that's a system with more than 60 flows or 70 flows or 70 tasks. That's how the point of view. And we compute the residual service and the deviation using either the staircase function or the fluid model or one of the two approximations, because you have seen in the term, I've got a quadratic term and a linear term. I may choose one or the other. Okay. And these are the results as expected. The staircase is always better than all the others. Okay. And the worst is always the fluid model. And in between lies the linear model and the quadratic model. So there is a gain, which is not so huge, but okay. This is just a normalization. Assume that the fluid model is the reference one. Okay, where are we far away? So we can see that the staircase model is in general half of the fluid model, and the quadratic approximation allows to gain 20% around. And the computation time, of course, the staircase model require more time, especially in this version, because you have to compute, you have to handle the least common period of all tasks or of flow, and can be big, whereas you do not have this problem with the other approaches. Take care that this is a logarithmic scale. So these are numbers, okay. You have details in the paper. And okay. So as a conclusion, okay, a new trade-off between accuracy and computation time. It was okay. It was done 1 year before Nancy was published. So, but such expression can be quite easily expressed, implemented in your tool if your tool just handle linear expression. Perhaps also for linear programming or so on. Don't know. I didn't try. And I think that's all.
You can sing a little bit. Yeah.
I can do some advertisement for RTNS if you want. No, I have sent the message on the Slack.
When you say a stair is the case that you take into account the stair level curves and also resulting service curves.
Yeah.
And in the quadratic is linear arrival curves and service curve, or is the stair arrival curves and
Sorry to interrupt, but if you...
the question is, it's only the linear analysis where you replace the service curve only by this quadratic service curve, or is the stair analysis that you replace the service curve?
I do not remember. I expect I have chosen the staircase one, but sorry, it's okay.
I have another question. Regarding the two things that we found mistake when using COP, the second one, I didn't get that it was a case that, for example, we didn't succeed to prove let's say, a negative jitter.
Yeah.
That you say it's you removed it.
Yes.
Or you found the bug. I mean, you found somehow.
So no, we didn't fix it in sense that I don't know if the result holds with negative jitters or not currently. I have done some experiment. Okay, you just set some random values and it seems to work. So I'm confident, but
Yeah, just you didn't manage to.
Yes, yes.
Yes.
So you mentioned 2 weeks to write it in the code. How long will it to compile or check?
A few minutes, something. Yes.
But it's in French.
Yes. So they are trying to change the name. Okay. So in fact, the point that's a kind of English people have defined the basic unit of computer science as a bit. Okay, and the bit in French is the same as a coq in English. Okay, exactly.
But not the other way around.
No.
Recorded, that's terrible.
So they are changing the name.
I have another more technical question. You show the linear approximation to a staircase.
Yeah.
Sure, that's the one that's closest, but in fact there are multiple ones that are not comparable. The one you showed was the one that has the largest rate. But
Yes.
there is also one that has the lowest latency. And they're not comparable. So why did you choose one? Yeah, so the dashed function, you could have another dash function that has a lower rate, but has a smaller offset on the.
Yes.
What's the rationale for choosing which?
Because before reading your paper, I was thinking that there was only one way to think. And then, yes, I say, yes, we can optimize also and change. For me, as an engineer, you cannot change the slope. Okay, that's a kind of, but okay, mathematically, yes, there is another one. And
There is more than one.
yes, there are, okay. So that's the one that has the same slope, yes. And moreover, I do not claim to have equality. I do not claim that this is the better one, the best one. In all experiment, we have a point where we have at least one point with equality. But I have currently no proof that such equality always exists.
There's a question on Zoom.
So, is there any comparison with the ground truth?
Is there any comparison with
The ground truth, I think it's
ground truth?
figures to the figures.
What is the true worst case?
With the true worst case.
Yes, I think that is what is meant.
Probably.
Let's assume that's what is meant. You don't know.
Of course not, in fact.
That's why we work with bounds. Otherwise, we wouldn't.
But even more, so that's a residual service, okay? And if the flow of interest has, for example, in this slides, packet of size 2, we clearly see that at 2, we do not have equality between both. Okay, so we can perhaps construct a system where the real worst case is equal to the bound that match this point, but with the linear approximation, we are not at the point.
Thank you. Yeah, thanks. This concludes the session.